Okay, so let's continue on section 2. So what we were doing was we were parameterizing the functions that made up the path. The last problem that we did was we had these 3 linear segments from 0, 0 to 5, 4, and then constant x equals 5, and then constant y equals 0. And we had to have it so that it was piecewise continuous, such that the parameter t at this point was the same as the ending of this segment t was the beginning of the next segment t, and the end of this segment t was the beginning of this segment t. And then ultimately you take those, you integrate across those values of t, and you use the parametric representations of the lines in this case to substitute in for x and y, so it becomes a function of t, and you also have the square root of dx dt and dy dt. And you multiply by dt, and then you have to integrate it, whatever that is. In this case, because there were line segments, I think you ended up with fairly simple integrals. You'd end up with integral of t squared. Here you'd end up integral of negative t, and this one was 0 because this term was 0 in the description of the line. So I think what we're doing was we're looking at this next example. So we're going from the origin to 1, 1 along this path y equals the square root of x, and then we're coming back from that point 1, 1 to 0, 0 along this straight path. And again, we're just trying to parameterize it, but I think ultimately we'll also see how we'd set up that integral. I think the first segment is always fairly straightforward because you let t equals 0 at the beginning of this interval. So what you would do is you let x equal t and y equal the square root of t. So if I plug, if I took these two parametric equations and eliminated the parameter, I'd end up with this path. And in this case, I go from t equals 0, such that I get 0, 0, and then t equals 1, I get 1, 1. So the vector representation of that path is x times the unit vector I plus y times the unit vector j. So x is t and y is the square root of t. So that's the limits on t. This would be x, this would be y in this case. And then I would multiply by the square root of the derivative. So if I go back to this, I take x prime of t and y prime of t. So I take those parametric versions, the ones that I use here, take the derivatives of them. In this case, because one of the segments is not linear, the derivative is going to be a little more complicated. So let's go to the next one. So we have this path 2. So this is path 1. This is path 2. It is linear. So we can do what we did last time. You can say that at t equals 1, which is the end t value for the first path, x equals 1 and y equals 1. And you can plug that into the parametric form of a line. And you can only do this with lines. So you plug y equal 1, t equals 1. There is no x in this equation, so you end up with 1 equals a plus b, and if you do the same thing for the x equation, you have parameters c and d, constant in front of t, and this constant by itself. So you plug x equals 1, t equals 1. You get two equations, you get one equation and two unknowns, one equation and two unknowns. So we need another equation. So we set t equal to something else. Now, We don't have to set it equal to 2. We could set it equal to 25 if we wanted to, and that would be reflected in these equations. So it would work out, but it kind of makes sense just to kind of be consistent with the original integral. But again, this t at the end of the interval is somewhat arbitrary. So again, you plug in x and y, x and t into here, so you have y equals 0, t equals 0, t equals 2. And so you get 0 is equal to 2a plus b, and then you do that for the x part. X equals 0 from here, the point, the final point, t equals 2, you get c plus d equals 0. And if you solve those two equations using elimination, you get a is -1, b is 2. I think you get the same thing. C is -1, D is 2. So those are the parametric equations for x and y. So what would they be? They're probably on the next page. Let me just insert them here. You'd have y is equal to a, which is -1, so you get -t, plus b plus 2, and you get x is equal to c times t plus d. C is -1 again, and plus 2 is d. So you get the same equation. So there they are. So you can write -t plus 2 is 2 minus t, and the same thing here. So the equation for the path as a vector is the x component is 2 minus t and the y component is 2 minus t. And the parameter goes from 1 to 2. So we can set up two integrals to do this integral along this closed path. So the first integral would be from t equals 0 to t equals 1, 4 times x, which was t, times y, which is the square root of t. Then you take the square root of the derivative of this with respect to time, which is 1 squared, plus the derivative of this with respect to time, which is 1 over 2 square root of t, quantity squared. And then you multiply by dt. And then the second path, which is a linear part, you can integrate from t equals 1 to t equals 2 of 4 times x times y times the derivative of this, which is derivative of this is -1, and the derivative of that is -1 as well. And this integral would be fairly easy. This one, I'm not so sure how to do that. Okay, let's look at another one. Find the total mass of the wire with the density defined as x plus y. So this is my f of xy. And I guess this must be a density per length, because if you didn't, then it wouldn't work out as far as the integral is concerned. So you've got position, which would be in meters, and both x and y. So you add these together, you get, well, you don't get meters, but you'd have some kind of constant which would convert the meters times probably density per meter, I would think. And we're going to follow this curved path. So this path here is actually already in parametric form. You know, another way of representing this would be r is equal to probably the square root of 1 minus x squared times I, something like that, I would think. Just thinking about it, the x coordinate, or t, is that right? Actually, you wouldn't do it as a function of t. What would you do here? Actually, I think you'd have x here, and you'd have the square root of 1 minus x squared j, because the y coordinate would be the square root of 1 minus x squared for a circle 1 radius. But they give it in parametric form initially, so I just wrote that out so that Now in this case we just have one equation, one integral. So from our curve, our vector defining the path of the curve, x of t is the cosine of t, y of t is the sine of t. So the derivatives of these are, the derivative of the cosine is negative the sine, the derivative of the sine is cosine. This is your positioned vector. The density is x plus y, but this is x and this is y. So we're going to put in, for x we're going to put in cosine t, for y we put in sine t. To do the ds part, in terms of this parameter t, you take x prime of t squared plus y prime of t squared. And you see what happens in the parentheses here, or in the square root, is you get sine squared plus cosine squared, and that is equal to 1. So this just becomes 1. So you just have the integral of cosine of t plus the sine of t dt from t equals 0 to t equals pi. So integrate the cosine, which is the sine, you integrate the sine, which is negative the cosine, you evaluate the upper limit of t, subtract evaluating at the lower level of t, so you get the sine of pi minus the cosine of pi minus the sine of 0 minus the cosine of 0. So the sine of pi is 0, the cosine of pi is negative 1, the sine of 0 is 0, and the cosine of 0 is 1. So here you get negative of a negative 1, so that's positive 1. Here you get negative of a negative 1, it's positive 1. So you add together and you get 2. So that's the answer. Okay, so that's examples of finding the line integral of a scalar function of x and y. Now, for the line integrals of vector fields, probably the most common example or most useful example is calculating the work. And so the work is going to be the integral of the force vector dotted with the ds vector, where the ds is associated with the path that you're taking. So I'll just read it. So we're not just interested in the product of the function f of x, y, z, which would be the force vector, and the length ds. We need the component of the force vector in the direction of this ds vector. So the question is, how do you do that? So you're going to be given a force vector, function of x, y, and z, or x and y, depending upon the number of dimensions. And then the ds vector, we're somehow going to have to figure out how to write that. You know, in this one we have the square root of x prime of t plus y prime of t. So it's probably going to be some kind of parameter. We're probably going to parameterize this expression just like we did here. But what we need to do is do this dot product. And the dot product gives you the component of the force vector in the direction of the ds vector at any point in space. So here's just an example. Here's our path. And as you go along the path, you have these ds vectors that are tangent to this path. It's ds vectors, which also, remember, another thing that's tangent to the path is the velocity vector, the derivative of the position vector with respect to time. And let's say this is the force vector at this point in space. So the component of the force vector in the direction of the ds vector is this. So you break it up into two components, one that's parallel to the direction ds and one that's perpendicular. And this angle here would be 90 degrees. So we're going to multiply this component of the force vector by this ds vector. And it's going to be a dot product. So it's what the dot product does is it basically finds this component mathematically instead of having to use geometry. Now here's the second case. We have this other force vector, which is not exactly the same as the initial vector. So it's changing. F is changing with space. And So this is my ds vector, which is tangent to the curve. So this would be the component of f in the direction of ds. This one would be the one that's normal to it. So I want to take this force and multiply it by this ds. And then finally, this, so you can see the force is kind of curving a little bit. So this is a force vector. Here's my ds vector. This would be the component of f in the direction of ds. This will be the one that's normal to it. So this is a graphical representation of a curve in space. This would be the force vector, and this is showing this force vector is, in this case, it looks like it's constant. So what you would do is this t is the unit tangent vector, and what we want is what is the component of this force in the direction of the unit tangent vector. So the first thing you do is to get the magnitude of this vector is you take the dot product of the force vector with the unit tangent vector. And then to get the direction associated with that length, you multiply by the unit tangent vector again. So this is a vector times a vector dotted with the vector gives you a scalar, and then you multiply the scalar by the direction associated with the unit tangent vector. So it turns out that the ds, the length ds, is the unit tangent vector times this increment in length. This is a scalar. This gives you this changes the scalar length into a vector ds. So t is this unit tangent vector for the trajectory r, and that turns out to be the derivative of the position vector with respect to time divided by the magnitude of the derivative of the position vector. So this is like velocity, and this is the magnitude of velocity. So if you divide a vector by its magnitude, you get the unit vector. And in this case, because the derivative is always in the direction of the path, then we use this unit tangent vector. So what we have is the work is the integral over this curve in space of the force vector function of x, y, and z dotted with the unit tangent vector times ds. So this is the ds vector. And what we can do is we can write the okay, what are we doing here? Okay, so there's two things we're doing here. Is this part is the unit tangent vector. It's the derivative of the position vector divided by the magnitude of the derivative of the position vector. The ds, we can change that to in terms of into this parameter, which we said we're probably going to have to parameterize this thing. So this ds here is a scalar, and the magnitude here is a scalar. So a scalar times dt is still a scalar. And then finally what you do, these cancel out, these magnitudes. This comes from the unit tangent vector, and this comes from changing ds into a differential involving dt. Those cancel out, so you get the force vector dotted with the derivative of the position vector times dt, but that is, we can call that a dr vector. It's the derivative of it's a differential of the position vector. Okay, so putting that all together, the definition of the line integral of a vector field. First, you have to have f, the force. Well, we're saying it's force, but it can be any vector. The f vector, the field vector. Be continuous vector field defined on a smooth curve C given by r of t. So the path is r of t, and it's a parameterized path where it goes from t equals a to t equals b. The line integral of f on c is given by, drum roll, this. So you integrate over the path of f dot dr, which is also the integral of f dot the unit tangent vector times ds. But this is the more useful form. So it's going to be the force vector, which we're going to parameterize just like we did with the f of xy when we integrated not in a vector field but in a scalar field, dotted with the derivative of the position vector times dt. So we can, if we have r as a function of t, we can find r prime as a function of t. If we use that r of t to rewrite the the vector field as a function of t, then we take the dot product. That dot product will give us a scalar, and we integrate the scalar function of t with respect to t from t equals a to t equals b, and we get the answer. Trying to see what this says. I mean, you know, in physics, instead of doing this line integral stuff, a lot of times we just found the component of the force in the direction of the movement, and in most of those cases we were moving in a straight line, and so it was simple geometry. In this case it's not simple geometry because the force vector can be changing with respect to position, and the curve is defined, but it's you know, if we want to go from point A to point B, one point space to another point space, there are many different curves. So I think what this is showing is just showing that, you know, at every point on this curve, that this product, which is reflected in the definition, gives you the component of the force in the direction of the unit tangent vector. Okay, so let's just do a problem. So it says integrate the force vector along this path, and so the force vector is, we're just going to do a two-dimensional version here, is going to be xyi plus yj. So it's already parameterized. Well, it's not really, no, it's not parameterized yet, but it is not. There's nothing. It's just a vector field. And the curve is defined by r, and that's equal to 4ti plus tj, which I think would be a straight line that goes through the origin and has a slope of like a fourth or something like that, I would think, just because this is just a function of t, and this is just a function of t. It's not t squared, or anything like that. And we go from t equals 0 to 1. So this has already done some of the work for us. So x of t is 4t, y of t is t. So what we do is you take the x and y values from the path and plug those into the force vector, so that, or the field vector, so that becomes parameterized. So for x we put in 4t, for y we put in t, for y we put in t. So this is f. And what we need also is we need dr is going to be r prime with, so dr dt times dt. So we have to take the derivative of the curve vector defining the curve, the path. So the derivative of 4t is 4 and the derivative of t is 1. So, and we go from t equals 0 to 1. So our limits of integration are from 0 to 1. This is the force vector. This is the derivative of the position vector for the path, and then we take the dot product of those. So you take 4t squared times 4t, which gives you 16t, and you take t times 1, which gives you t. So now we're a scalar equation. We could just use single variable calculus to solve this. So the integral of t squared is t cubed over 3. The integral of t is t squared over 2. Evaluate it at t equals 1 and t equals 0. At t equals 0, it goes to 0, so we just need to evaluate it at t equals 1. So you get 16/3 plus 1/2 and find a common denominator, and you get 35/6. Okay, so that's how that works. So let's look at another problem. So we've got the force vector field is x squared I plus xyj. The path is 2t I plus t minus 1j. And we're going to go from t equals 1 to t equals 3. And what I'm doing here is just going to draw this path. So you can see at t equals 1, you get 2i plus 0j, which is just 2i, which means it's x equals 2. And if you plug t equals 3, and you get 2 times 3 is 6. 2 minus 1 is 3. It's just 3. So 3 minus 1 is 2. And if I draw that, that's this path. Is it this path or is it the other path? No, it's actually this light purple line. So that's the path going from here to here. So it's straight line. These other two are just the, I'm not sure why I had this in there, to be honest. Anyway, that's final position. I know what it was, because this is the initial position vector. This is the final position vector. This is the path between the beginning and the end. So that's why it was in there. Okay. So this part you didn't need to do. I just did it to see what the path looked like. So we need r prime of t, and we need to parameterize the force vector. So the derivative of r1 of t, I think it's 1 because if that was the first part of a multi-part path. I think we're going to actually come back the other direction. So we'll do that in a second. But let's finish this off. So derivative of 2t is 2. Derivative of t minus 1 is 1. So you get that. X is equal to 2t. So you square that and you get 4t squared I. X times y is this times that. So you get 2t squared minus 2t j. So we take the force field vector dotted with the derivative of the position vector. So you get 4t squared times 2, which is 8t squared. And you get 2t squared minus 2t times 1. So we add these two together. Now it's just a function of t. We integrate from t equals 1 to t equals 3. And so the integral of t squared is t cubed over 3. The integral of t is t squared over 2. In this case, we have to evaluate it both the upper and lower limit. So I ended up evaluating this at the upper limit. So I get 10 times 3 cubed over 3, and subtracted at the lower limit, 10 times 1 cubed over 3. And then I subtract, that negative sign goes there. And I've got just t squared, so if I cancel out the 2's here, so I get 3 squared minus 1 squared. And you do the fractions. Well, you get 270 over 3 minus 10 over 3 from here, and here you get 9 minus 1, which is 8. And then you find a common denominator, which should be 3, and you get 236 over 3. And this is not divisible by 3, so that's as simple as you can get. Now, the question is, let's go back from here to here. So we're going to go the same path. We're still going to go from t equals 0, but instead of going from 0 to 3, we're going from 0 to 2. And we're going to use these as the equations that define the curve. And you can see if I plot some points here. I really don't need to do that many. T equals, say, 0 and 2. That's about all I have to do. And if I put x and y, x is going to be, at 0 you get 3 minus 0 is 3. 3 times 2 is 6. So you get 6. And you put 0 in there and you get 2. And that's my initial point, which was the final point from the past point thing there. And then if I plug in 2, I'll get 3 minus 2, which is 1. 1 times 2 is 2. And if I plug 2 in there, I'll get 0, which is that point. So that does properly identify this path. It's going the opposite direction, though. So what we should expect is the same answer, but a negative sign because of the path, the direction of the path. If you go one direction, you get a number. If you go the opposite direction, same path, you get negative. It's kind of like with, if you have some object and you move it this way in a force field, you increase the potential energy. If you go the other direction, you decrease the potential energy. So, again, we need the derivative of this path 2. So we take the derivative of here, and the derivative is negative 1 times 2, so you get negative 2. Here it's negative 1. So that's the derivative. You rewrite the force vector in terms of these parametric representations of the path. So this is 6 minus 2t. So I get 6 minus 2t squared because I had x squared I. Here I take x times y. X is 6 minus 2t. Y is 2 minus t. We dot that with the derivative of the vector representing the path. And if you square this, you'll get 36 minus 24 plus 4t squared. And then if you dot it with negative 2, so that's where the negative 2 comes from. So I've kind of combined a few steps here, but negative 2 times this squared is 36 minus 24t plus 4t squared. Same thing here. You take negative 1, that's where the negative sign comes from, and then if you multiply this out, you'll get 12 minus 4t plus 6 or minus 6t, because this is a negative sign. It's kind of a short negative sign. That's a negative sign. Negative 6t and then positive t squared. So if you multiply all this stuff out and then combine like terms, you get to this expression. So we integrate that. So this becomes t, this becomes t squared over 2, this becomes t cubed over 3. And I don't know why I put a 2 there, so we'll fix that. So it's t cubed over 3. And you evaluate the upper limit, which is 2, and you subtract the lower limit, which is 0 evaluated. So you'll get negative 84 times 2 plus 58 times 2 squared. Oh, yeah, so 58 divided by 2 is 29. Here you get 10 thirds and then 2 cubed. And if you go through all the math, you get negative 236 over 3, which is exactly the same answer that we got with the last situation, except that there's a negative sign because we're going the opposite direction. So what this demonstrated was that I think this has, I don't know if this has to be a conservative field for that to happen. I think it does. So we'd find out that that field is conservative if we looked at it. And also that, how we parameterize this is, it's kind of up to us as long as it's consistent. Now, one thing we didn't have a continuous, we had two different problems. Well, we still would have gotten 0 if we'd added these two things together. If we started here, went to there, and came back, we add those two integrals together, we get 0. So, okay, so that's one way of solving them. The second way is to do line integrals in the differential form. So we take the form of the equation we had before, f dot dr, where dr is r prime of t times dt. So we can write r prime of t as dr dt, and you see the dt's, well, we don't cancel out the dt's yet. This derivative is, the derivative of the position vector is just the derivative of the x component times I plus the derivative of the y component times t. And if you then dot this out, so you get m times x prime of t and n times y prime of t times dt, and then you convert back ultimately to dy and dx. So what happens is x prime of t is dx dt and y prime of t is dy dt, but you can see these dt's cancel out and you get this. So what this is, it's the same expression except it's in differential form. So you can solve these problems two ways. And m is the what is m? M is just the x component of the field vector, and is the y component of the field vector. And so in this case, you don't have to convert them over to parametric form, which can be useful in some points. So here's an example. So what we want to do is we want to integrate 2x minus y dx plus y plus x plus 3y dy. And what that implies is that the field vector is 2x minus yi plus x plus 3y j. And we want to evaluate the integral along the path y equals 1 minus x squared, which is a parabola. So it's a parabola, it's inverted because of the negative sign here. It intersects y equals 1, has x-intercepts of -1 and +1. So you can see the integral, we want to integrate from here. So this is from x equals 0, y equals 1 to x equals 1, y equals 0. And it's in that direction. So I put an arrow. So let's just follow along. Then we'll comment on it. Because I just mentioned I didn't think you had to parameterize it, but I think you do have to. We'll see what happens here. So first is to write c in terms of t. So when we have just this one curve, you can usually set up this parameterization pretty easily by letting x equal t and then y equal 1 minus x squared or t squared. And if we calculate dx, take the derivative of t is 1 times dt to get the differential. Same way here, you take the derivative of this, you get -2t, and so then you'd add the dt to it. Now the position vector is just the x and y coordinates here, the x and y values parameterized. So this is r. So you get t times I plus 1 minus t squared times j. The derivative is I minus 2tj. So this is using the, so I guess in this case we're using the non-differential form, and then we'll use the differential form, I think, to show that they're the same thing. So this is your force vector, your field vector. This is the derivative of the position vector. Then you take the dot product. So if we do that, we get 2y minus x, 2x minus y dotted with I. Now one thing we haven't done here is this part is not in parametric form at this particular situation. So let's just see what happens. So what you get is 2x minus y dotted with this part, which is 1, times dt. And then you get x plus 3y times negative 2t dt. Now this dt part is dx, and this dy part, this part here is dy. So this ends up being m dx plus n dy. So what I've done here is actually what we're going to do is I see it's 41 minutes, so we're going to stop there and we'll continue this on next time. Let's see how much more we got in this section. I think it's just showing you chemical. Well, that's almost the last thing. So we'll finish it up, but let me show you the homework assignment so you can have that. Start working on these. So we just got a little bit left, and then we'll move on to the next section. So those are the homework assignments for section 2.